All right, let's look at an example for part 1. An advertising firm is interested in determining how much to emphasize television advertising in a given county. The firm decides to conduct a sample survey to estimate the average number of hours per week that households in the county watch television. Suggest a survey design for this problem. Okay, we know that the county, some of the background information is also given. We know that the county contains 2 towns, town A and town B, and some of the surrounding rural area. We're also given that town A is built around the factory. Most of the household contain factory workers with school-aged children. Town B is an exclusive suburb of a city in a neighboring county, contains older people with fewer children at home. And so we know that town A and town B, and of course the rural area, they are quite different in terms of the time that they would watch TV, because of the living could be quite different, or the living habit would be quite different. So we know that there would perform a heterogeneous between strata. And within a stratum, they could be quite similar. So we would suggest using stratified random sampling. So a stratified random sample with 3 strata appears to be an appropriate sample survey design. And then we give reason of that, because between strata, they are quite heterogeneous. Within stratum, they are homogeneous because they, with the workers and the school-age children, they usually watch TV in the evening. And town B, for the older population, they have a different watching TV habit, but within the town B, they are quite similar. So homogeneous within stratum. And of course, in the rural area, it is quite different from town A and town B. So, of course, because of the administrative convenience and the time and the similarities in behavior and patterns within each group, so we would suggest to use stratified random sampling. Okay. Estimation of the population mean. Okay, so by definitions and the notation, we can calculate the population mean, capital Y bar. This is going to be the true population mean. So imagine the true population means it's indeed we add up every individual within the stratum, and then we add up each of the we add up all the total of the strata and divided by the total population mean, the population size, right? So each of the individual within the stratum L, and then add up all of the stratum population. Then we add up the total number of strata, L from 1 to capital L. So that would be the total for the population. Then we divide it by the population size. So we would be expecting the true population mean, right? Or alternatively, we can multiply by NL, also divide by NL. And if we just look at this bit, it is the stratum total divided by the stratum population. So this would be indeed the true stratum mean, or the capital YL bar. And what we have in here is the weighting for a particular stratum, so capital WL. What it shows is that the true value of the population mean is indeed the stratum true mean, adding up together, weighted by the population weightings. Okay, so on the other hand, under stratified simple random sampling, we can estimate the stratum true population mean by our sample Y bar L, because we know that within each of the stratum we perform a simple random sampling, like chapter 3. So little Y bar L is an unbiased estimator for the stratum true mean. In this case, we can replace this capital Y bar L by our sample y bar L, little y bar L from our sample. In other words, it shows that if we conduct a survey, a simple random sampling, within the stratum, we estimate the stratum average, we can add them up together, weighted by the population mean, and this would form the y bar from our sample. And this would be the unbiased estimator for the population mean. And we use a sub-index ST to indicate this is a mean estimated from stratified random sampling. Okay, so we show that this is an unbiased estimator for the population mean. For the variance of this estimator, so we said that if each of the stratum, they are independent with each other. So we are treating like adding up the independent population. In this case, for the variance of A y1 plus B y2, if y1, y2, they are independent variables with independent distribution, the variance of a constant A would become A squared, variance of y1, plus B squared variance of y2, because y1, y2, they're independent. Okay, so if that's the case, we can find the variance of our y bar under stratified random sampling is indeed equals to summation of capital WL. This is a constant, so variance of a constant that becomes constant square. So this becomes the capital WL square multiplied to each of the variance of the stratum. Okay, variance of the stratum mean, we can treat it like a simple random sample, like chapter 3, could be replaced by the final population correction factor multiplied to sigma L squared over our sample NL. This is the equation for the overall variance of our y bar under stratified random sampling if each of the stratum true variance sigma L is known. If each of the stratum variance is not known, we can estimate these sigma L squared by our sample variance. Okay, so that means we can estimate the variance of our y bar under stratified random sampling. So we have a hat on top of the variance. Again, that equals to the summation of the weighted square multiplied to the estimated variance of the stratum y bar. Again, this is estimated, so we can use a final population correction factor within the stratum multiplied to our sample SL squared divided by our sample NL. Right? Okay, so we just proved that again. Equation 4.3 shows that the y bar under stratified random sampling is estimated by the weighted summation of each of the stratum y bar adding together weighted by the population mean, or we can replace NL equals to the total population multiplied to the weightings. So if that's the case, we can we write equation 4.1 by actually multiplying the NL to the average, so that becomes the stratum total, adding up all of the stratum total by all the strata divided by the population size could also result in our y bar estimate. Okay, so another version of the estimated variance, again replacing the capital YL, we can have our total variance adding together and divided by n squared. Let's go back to example 4.2. Suppose there are 155 households in town A with all the factory and the school children, 62 households in town B, the elderly, and 93 households in the rural area. And the advertising firm interviewed 40 households. And then we find that sample size in the Tang A is 20, and then we sample 8 households from Tang B and 12 households from the rural area. And then we have the we call this a proportion allocations, because out of the 3 Tang we have 155, 62, and 93. So in proportional, the larger Tang we would collect more of the sample, and the smaller of the Tang we would relatively collect fewer of the sample. So N2 would be relatively smaller than N1, and for the rural area we have a medium size of the populations, then the samples would be in the middle. Okay, so this is called the proportional allocations. The measurement of the television viewing time in hours are shown. Okay, so Tang A, we ask 20 of the household, so sample size is 20. The population size is 155. On average, in Tang A, they watch about 33.9 hours per week, and the sample variance is 35.358. We call it the same for Tang B and rural area. We can make use of this data to calculate the average television viewing time for all of the household in the county, so for the overall population. Secondly, we can estimate the average television viewing time for Tang B, so we're looking at the subpopulations estimate. And then we look at the average difference between Tang A and Tang B. We might want to conclude if there's any significant difference between Tang A and Tang B people of their average TV viewing time, right? So solution for our first question, what is the overall average for the populations? We can use the total watching time, adding up for the 3 Tang and divide by the total population. Or we can add up the average Y1 bar, Y2 bar, Y3 bar weighted by the capital omega, capital WL, which is 155 out of 310 multiplied to 33.9 plus 62 out of 310 times the average plus 93 out of 310 multiplied to 19. It's similar, same. And then we can estimate the total population average hours of watching TV is around 27.675. We can estimate the variance of my Y bar under the stratified random sampling. Okay, so if that's the case, we add up the variance of each of the Tang multiplied to the finite population correction factor, multiplied to the population size square, and divide by total population size. So basically, the estimated variance is about 1.97. Taking to the square root is 1.403. Now we can construct a 95% confidence interval for my point estimate. Okay. Question 2. If I just interested in Tang B, so it is very much like performing a simple random sample from chapter 3. So we have the Y bar average. Tang B is calculated, it's given 25.125. Then based on the sample variance SL square, multiplied to the finite population correction factor divided by the sample size, we can find the standard error is about 5.031. Again, with this estimate, we can construct the 95% confidence interval for Tang B. Okay. Thirdly, we want to ask whether Tang A and Tang B, Tang A with kids and factory workers and the elderly, in Tang B, whether they have a significant difference in the hours of watching TV. So using Y1 bar minus Y2 bar, because Tang A and Tang B, the data, they are independent, then we can simply use the same technique that we did in chapter 3. We look at the variance of the differences of 2 mean is indeed adding up the variances. So this is around 26.843 for the variance. So taking the square root, this is 5.181. Okay. With these point estimate, we can again construct a 95%